Hello, good morning everyone. Thanks a lot for attending the talk. It's a wonderful workshop so far. I hope all of you are enjoying it as much as I am. So I'll talk a little bit about how neuromorphic technologies can help intracortical brain-machine interfaces. Some of the slides are common to the work group introduction that I gave early on, so apologize if you have seen it earlier. Some of you here at IISc may have seen some of these slides last year at the Brain Computation Learning Workshop. So again, apologies, but there are some new stuff, so hopefully you'll not be totally bored. Okay. So a little bit from about where I am. I'm currently at Hong Kong, so beautiful city. So if you are visiting there, just drop a note. Please feel free to drop by our lab. Especially if you are attending this workshop, it's a good way if you're going back to the US, for example. Like Toby is doing that. He's going to stop in Hong Kong and go back. So it'll be nice if you can also do something like that in future. So my group works a lot on, again, the topic. Oh, he's going to Australia? Okay, yeah. Fair enough. So if you're going anywhere, Australia or US, you can go through Hong Kong. Okay. So my group works a lot on, again, the focus of this workshop, neuromorphic systems, circuits, and algorithms. And we look at two applications. One is brain-machine interfaces, which is what I'm going to talk about. We do a lot of other things related to, I'm broadly writing Internet of Things, but we do a lot of chips for processing devious data. We do a lot of chips for keyword spotting kind of things and so on. So I won't talk about that here, but if you're interested, we can chat about it afterwards. Okay, so I'll start off by talking about what are intracortical brain-machine interfaces, and then we'll go from there. Okay, so this is the brain-machine interface is a system where you are trying to record data from the subject's brain, and the recording can happen at different levels. For example, you can record from the scalp, which is like typical EEG. You can also record from the surface of the cortex, which is like ECOGs, or you can have penetrating electrodes that are going into the tissue, which are more like intercortical microelectrodes, and that's what I'll talk about mostly. But what's going on, what's the trade-off? The trade-off generally is, as you go from EEG towards intracortical, your resolution, both spatial and temporal, keeps on increasing. So you have improved control or performance in the BMI. It's also useful for fundamental science because you can record from single neurons. But of course, there's a trade-off. So obviously, there's extra risk because of the increased invasiveness of these technologies as you go towards the right. Okay. So generally what happens in intracortical systems is you have probes like these which are put inside the patient's brain. For example, in this case, you have a patient who is paralyzed, who can't move their hands or legs. And using these brains and special custom electronics, we can actually record the person's brain data. And with some training, we can actually get a data set from which we can decode what the person is thinking. Okay? So for example, in this case, the person is being trained on a task where they can move a cursor on a screen, and they can use this to, let's say, communicate by spelling different words, communicate with another person. They cannot speak by themselves. Or they can use this to move a wheelchair, or they can use this to move an artificial arm and so on. Okay? So the connection can be from the brain to any kind of machine. So that's why it's a brain-machine interface. Okay, so going back to that earlier picture, so if you want to see how much improvement can you go by going towards the right, towards more invasive systems, early days EEG spellers could do about 1 to 5 characters per minute. Okay. So as you move further down, the early systems for intracortical could do about 40 characters per minute. The very recent systems, I'll talk about this a little bit more, have pushed this up to about 90 characters per minute. Okay. So if you're thinking, how does that compare with how you guys type? When you are typing on your smartphone, smartphone typing is about 115 characters per minute. Just to put it in context, since Ernst did this talk, I decided to put in this blurb. How do you convert this to bits per second? Okay, so it's roughly you have to divide by 12, right? So alphabets is about 26 alphabets, about 5 bits, and 60 seconds in a minute. So 60 divided by 5 gives you a factor of 12. So if you divide this 115 by 12, roughly 10 bits per second, going back to Ernst's talk. So amazing, yeah? Everything goes back to the 10 bits per second. Okay, so you can clearly see the benefit, right, to going towards intracortical. But again, keep in mind there's this risk of extra invasiveness. So patients would do this only if they have no other choice. Okay, so a little bit closer look at IBMI system. What goes on here is you generally have these head stages. You had a wonderful talk earlier by Arun. You would have seen the sort of head stages that he showed. And then these head stages actually connect down to these implanted systems. Okay. So what happens here is you can see there are wires connecting from this head stage to the PC. Okay. These are very bulky. It does not allow the patient to move. Right? So Arun was talking about removing these wires, right? And there are also wires connecting from this head stage down to the implant. So what that means is the head stage always has to be there. There has to be sort of an opening over here, and that always keeps a risk of inflection. Okay, so generally what we hope to do is if we can remove all of these wires, we can go towards a wireless IBMI. That would be ideal for the patient. So the question now becomes, what are the challenges for wireless IBMI? Okay. So think about it. If I have to remove these wires, I have to make this implanted thing wireless. So it has to communicate data entirely wirelessly through the scalp. Second part, if you want to remove these wires, you have to make it a wireless head stage. Okay, so this data from here has to go to the computer wirelessly. The system Arun showed, okay, it was wireless, right? So does it already solve this problem? If you really look at it carefully, what his system is doing, he is logging the data here on this head stage. At the end of the day, they will come and capture the data to see what data they got entire day. For a BMI, you cannot do that. The system has to react. There has to be a closed loop system, right? The system has to send data directly to the computer. The computer has to do something. The user will get feedback from what he sees on the screen and change his thoughts. Okay? So you can't do that. You have to stream the data continuously. It's a much bigger challenge. There have been systems that do wireless IBMI. This was a wonderful system, very early system from Brown, and there's a lot of details about how they did the encasing and so on. But basically what I want to show you is that for a 100 channel kind of a system, where these probes have about 100 recording channels, they were using about 24 megabits per second. The system could operate only for about 7 hours. Think about it. I at least get frustrated when I have to charge my phone, my smartwatch every day. Think about a patient who is using this device. If they can't use it for even one day, it's super frustrating, right? So one of the big challenges is how can I increase the battery life for this system and still maintain it to be wireless. The further challenge, well, it depends on how you look at it, is looking at this picture. This picture is sort of like a Moore's law for neural recording. Okay? For semiconductor people, everybody talks about Moore's law. What's going on is x-axis is like time, y-axis here is number of simultaneously recorded neurons. Again, this is a log scale. Okay? And basically what you see is you can keep on recording from more and more neurons as technology improves, so which is good for us. We are getting more information. But that's a bigger challenge for creating a wireless system because now your data rate is blowing up. Okay? So if you think about it, published wireless head stages, wireless implants are about here. Already we are recording at a much higher number of neurons. Okay? So there's a big gap here. So the question is, okay, what can we do to solve this problem? Yes.
When you say recording, it means that you are just saying how many electrodes? Or like when you say...
No, this is actually a number of neurons, so you're also doing sorting. Yeah. So it's about a factor of roughly 2 to 3 more. Okay, so the solution, so I think all of us here who are doing these neuromorphic circuits would say, oh, okay, you put some intelligence there, do edge computing. Okay, so if you do edge computing, no need to send the entire data, extract information from the data, and then that information bandwidth is a lot less. Potentially as low as 10 bits per second, right? So the solution then is to put some intelligence into the implant, and that's what we have been doing for the last 10 plus number of years, where we're putting some kind of machine learning co-processors inside the implant to reduce the amount of data that you have to throw out of the implant. Okay, so the next question, why neuromorphic? Why not something else? I guess at this meeting, I should not even be having this part, but let's just have this discussion. Okay. So, I mean, of course, I have to qualify about what I mean by neuromorphic. There's a lot of different variants of how people define it. If you look at the original paper by Carver, there we are talking about using analog or physical computing similar to the brain, because the brain is also using a lot of analog voltages, currents, ionic concentrations, and so on. So the hypothesis is if you can use these kind of analog or physical computing primitives, especially for these kind of pattern recognition or machine learning kind of applications, you would potentially get orders of magnitude benefits in energy and area efficiencies. So that's really, I mean, the original definition. I call it neuromorphic version 1. But since then, last 10, 15 years, a lot of people in different communities try to do different things and they call it neuromorphic. So I would broadly say in digital systems, you heard Rajit's talk, if you are having non-von Neumann architectures where memory and computing are kind of mixed, potentially people also call that neuromorphic. If you're using digital systems with low precision, a lot of people also call that neuromorphic. If you talk on the algorithm side, spiking neural networks as opposed to normal ANNs, where in this case SNNs, time is intrinsic to computing. In these kind of cases, computer science folks will call these algorithms as being neuromorphic and so on. Okay? So in this talk, when I talk about neuromorphic technologies, how can they help BMI, I will talk about some of these different examples of neuromorphic systems. Okay, so if you think about it, again, this is a discussion we'll have in this meeting, we have had in this meeting many times. What are good features for where neuromorphic systems are supposed to be very good? Generally, they're supposed to give you very low energy operation. Generally, we talk about real-time operation. So our brains are optimized for these tight sensory motor loops. So they should be good for systems where you have these kind of closed loop feedback systems. Again, we are very good at learning from few examples. If we show baby a few examples of an image, they can kind of generalize to other views, so on. So this is another thing where we expect brain-inspired intelligence to be good at. And lastly, we are good at processing signals encoded in time, right? So speech or video, anything that we are seeing, we are very good at processing that. Potentially then, if you have brain-inspired algorithms, they should be good at processing other time series data. So now think about this application of brain-machine interfaces. Low energy operation, is it a necessary thing? Of course it's required, because you're putting an implant inside the brain. Battery power is limited. You cannot open the brain and change batteries. So you want it to run for a long time. You want the system to have very low energy operation. Real-time requirement, is that needed? Yeah, it is needed, because again, this is a closed loop system. Based on the decoding that you're doing, the user is going to see what the decoded output is and change the BMI command based on that. So it has to happen in real time. Learning from few examples, is that necessary here? It's also necessary. If you have done any chronic recordings from the brain, you would see that one day we get sort of recordings from the microelectrode, the next day when we come back, the microelectrode would have moved a little bit due to micromotion, and the data that you get from channel 1 today will be quite different from the data that you get from channel 1 tomorrow. Okay, so every day when we come back to the lab, we have to recalibrate our decoders. And if you do this over a longer period of time, then there's of course some tissue formation on the probes, which changes the probe impedance, and again there's non-stationarity over a longer period of time as well. So indeed, for every day you need to recalibrate your decoders with few examples. Okay, so very deep models don't work generally very well unless you do some transfer learning kind of stuff, but again I won't talk about that too much. And of course the signals are encoded in time. You're getting real biological spike trains, right? There is no extra spike conversion overhead. You're really working on biological spikes. So in some sense I call this like a match made in heaven, right? It's perfectly matched. You would think that this kind of technology would be very nice for BMIs. Okay? And hopefully I'll show you some examples in this talk that convinces you. Okay. Again, this community, I shouldn't even be talking about this, but what if somebody says, what about digital ASICs? Why not digital ASICs? Why do you want to do neuromorphic systems? So this is a survey I did several years back, which is looking at different machine learning systems, conventional machine learning systems using digital or mixed signal. So red dots are digital, blue dots are mixed signal. X-axis here is energy efficiency, which is like, how many operations per watt can you get? Y-axis is throughput, how fast can you do stuff? So basically, good solutions should be on the top right corner, right? And what you see is indeed the blue dots here are far better than the red dots. Okay, so even for conventional machine learning systems, if you are using these concepts of analog processing and low resolution processing and so on, sparsity, you can actually get orders of magnitude benefit in energy efficiency. Okay, so that's why we are looking at these neuromorphic systems for very low energy implants. Okay, so now we know that we want to put some intelligence on the implant. Now, what are the sort of processing that is needed in this case? Okay, so I'll show you an example. A typical conventional system goes like this. From the probe, you have some amplifiers which amplify these tiny signals, the spike signals that you see, these kind of blips that you see here. These spikes can be anywhere from about 20, 50 microvolts to 200 microvolts. So you need to amplify them, then digitize them and transmit. Typically what happens on the other side, you will receive the data, you will detect these spikes. Then there is some step called spike sorting, which looks at the shape of the spikes and separate them into source neurons. And then you will pass it to a decoder that will again drive this actuator. Could be any kind of actuator. So if you do this, this wireless link consumes about 20 Mbps for 100 channel data. Thinking, okay, can I move each of these blocks to the left? Each of these blocks to the left. Okay, so if I move the spike detector to the left, then I will only transmit the samples corresponding to the spike. You can already get a huge amount of data reduction, about 100x. Okay. And this happens because the spikes are sparse in time. Okay, now if you move the second one, the spike sorter also here, so that you are not transmitting any raw samples, just the identity of the spikes, you can get another order of magnitude kind of reduction. Okay. Finally, if you can put the decoder in over here, you get another 2 orders of magnitude down over here. Okay. So it seems that if you put more and more edge computing down here, you can really drive down the data rate, which makes the wireless power go down, makes the wireless link also more robust. Okay. You have less bit error rates as well. But of course, there's a trade-off. A trade-off is, okay, as data rate is going down, your compute is actually going up. Right? So you have to make sure that you can keep your compute power within limits. Okay, yeah, there was a question.
So is this spike sorter digital or analog?
Good question. Is a spike sorter digital or analog? As I showed earlier in my earlier motivation part, we are trying to do something that's more neuromorphic solution, so it's not a pure digital spike sorter. Yeah, it's a mixture actually. Yeah.
So as you move,
actually, I will qualify that. In the work that I have done, we have actually removed spike sorter. We don't use it because the spike sorting actually is not so necessary for the decoding stuff that we are doing, and it actually adds more non-stationarity to the data. So just doing decoding is good enough, more robust. Yeah.
Also there's a trade-off, right? As you move more systems to the implant, if you do the decoding, your decoding power will increase, but your wireless transmission power will reduce.
Correct. So that's exactly what's shown here. The data rate is going down, but the compute is going up as you go down the chain.
How do you find a stable point like what?
Well, I mean, the thing is you have a certain area and power limit for your implant. Point is, whatever you can make that you can fit within that power budget in any of these situations, you stop there. Yes.
You showed them as symmetric, but is it really true that as you go an order of magnitude down in data rate that your compute goes up by?
No. The pictures is symmetric just for beauty.
Yeah, okay.
Yeah, for ease of drawing. It doesn't go up that way. Yeah.
Yes. Because that could help you find the optimum too.
In some sense, yes, but a lot of cases there are some hard constraints on the size of the implant. So even if your knee of your curve is somewhere else, you probably can't even get there. Yeah. Anything else? Yes.
How do you decide on the features?
Features.
Yeah, because like when you are directly transmitting, you get all the data, and then like you can run some algorithm and like okay decide upon it. But if you're shifting everything towards the implant side, then what sort of like how do you come up? Okay, I only need this feature or like that.
Okay, so I'll answer two things there. First thing is for these systems, the ones that we are doing, like I said, spike detection is always kind of necessary step. Okay, so this one we always do. For decoder, what happens is a general in the field, if you look at it, the commonly accepted feature is firing rates. Now, what is not known is the bin width. What bin width is optimal for your firing rates? There are several ways we optimize that. I'll show that a bit later on, but I will give you a caveat. For these systems, we always have an option of transmitting raw data out. So we never say that we will not have that mode at all. So we will generally have that mode. If needed, we recalibrate using that and then go back. Okay, so now coming to the main part, I'll talk about few examples where hopefully I'll show you some neuromorphic tricks, how they could be useful for BMI systems like the ones I showed. Okay. First one is at the front end, if you put a change detection circuit, pretty much like the DVS camera that you saw. Okay, so this is an example of a recording, and what you see here is these big peaky things. These are the neural spikes or action potentials. Those are the ones that we are interested in. Okay, so a lot of labs also use local field potentials, which are low frequency signals. In our case, we are not using that, so we are more interested in these kind of peaks. Okay, so if you see this, you can sort of see that, hey, if you are only interested in these signals, why would you want to send data corresponding to the others, right? So if, in other words, if these big signals, these big changes are the ones that you want, then potentially I can have a change detection circuit that sees if the change is bigger than a certain threshold, only then I will send that delta. So zooming in, so think about this as a particular waveform, and if I use a delta modulator like circuit that's looking at changes, put down the equations here, but basically intuitively you're looking at changes of the circuit, of the input. If there are positive changes, you can emit these positive or on pulses. If there are negative changes, signal going down, you can emit this negative or off pulses, right? And what you can see is, yeah, for this kind of action potentials or spikes, indeed you get a lot of these off pulses for this part, a lot of the on pulses for this increasing derivative, and again some off pulse for this decreasing one. Right. There are some other noise elements that are also triggering pulses, right? So it's not entirely true that only the action potential is gonna give you pulses. But if you can play some tricks, choose your thresholds in a good way, or maybe even do adaptive thresholding, you can reduce the amount of these spurious spikes and potentially just have pulses being generated for this part. Yeah.
But for a multi-channel recording, you need, if you have to do spike sorting, you have to, you can't just threshold it, right? Because then you will lose the information of the mixture, how the information is getting mixed together.
Not information getting mixed together. So for spike sorting, what you need is the shape of the spike, right? Generally what happens is you will have on the same probe different shaped neural spikes, and that is basically what you sort out to different units. So potentially what you can do is, even looking at this sequence of on and off pulses, you could recreate your spike shape to whatever accuracy you want. Whether that will be good enough to get spike sorting accuracy same as the raw signal or not depends on your delta step.
But let's say, okay, in one channel we transmit only during this time, but at the same time the next channel, the other channel might be silent, right?
That's true. So what we are doing, I don't know if I have it, what we are doing is really from these pulses we are creating a packet for a fixed period of time. So that packet is containing information of all channels, and in that packet you'll have a bunch of zeros for channels that are not firing, and then you can compress that and send it out. So it's not like you will not be able to capture other information. So essentially in the packet will have other information. And this may kind of answer your question. So basically if you have an array of these kind of front ends, you can effectively do stuff like the DVS. You can have arbiters that can send events out into an event queue, and you can either send out these pulses as and when they happen, or you can actually accumulate the pulses in a short period of time, create a kind of a mini rate, and then that can go into the packets. Okay, so this one we call it the all pulse mode, and this one we call the pulse count mode, or PCM. And the circuit here is kind of similar to DVS. You have a capacitive amplifier, which is also used in neural recordings, and then you compare it with thresholds, and then you can generate some request signal whenever it crosses the threshold, and so on. Okay, this is showing an example of neural spike and its reconstruction. So APM, the all pulse mode, is sending out the pulses whenever they happen. The PCM, or pulse count mode, is actually accumulating data in a small period of time and then sending it out. Right? Why we are accumulating that is potentially, you can save bandwidth a little bit more. Instead of sending the address for all the events, you send the address once for that whole bunch. Trade-off wise, if you are bunching too much, you lose the time resolution, right? So your reconstruction won't be as accurate. So you can see here the APM, the red one, kind of follows this spike pretty nicely, but PCM4, which is accumulating in a big 4 times T window, this dashed green line, the spike reconstruction is actually pretty off. That's kind of the trade-off. As a rule of thumb, how much compression can you get? These bottom curves show you that compression ratio versus frequency of action potentials. Of course, if action potentials are happening very frequently, your compression won't be as much, right? You have to send a lot of data. So these curves make sense, that the compression ratio goes down as frequency of action potentials go up. Yeah, go ahead.
Like for the pulse count mode, you are accumulating the events, right, corresponding to all the spikes.
Corresponding to spikes in a certain time window.
Okay, so how are you able to reconstruct the spike shape?
That's why the reconstruction is bad. So I don't have that timing information. So when I reconstruct in that entire time window, I'll just, suppose I had a pulse count of 4. I will just place the spikes equally spaced there. I don't have the information when exactly they happen. But still, you can see it's still pretty good. It's not that bad. And especially for us, because for our decoding, we are not doing sorting. We are just doing detection. This is actually pretty good. Yeah.
If you end up getting like a rapid series of events, how do you know if that's coming from a bigger amplitude spike or multiple spikes happening? Or does that not matter?
Multiple spikes happening, meaning in the original signal, in the original raw signal, you are saying if there were multiple tiny bumps?
Right, like if you were picking up multiple spikes, kind of like a burst, versus if you were picking up like a big spike that was nearby from a neuron that's nearby, do you have to then distinguish if your events are still encoding them as a rapid burst?
So if you have a rapid burst, you would have a sequence of on-off kind of thing, because it's going up, coming down, going up, coming down. So you have the information in the pulses that's coming out. Yeah. And actually, there's an idea we can actually use this put it into some of the dendritic circuits and do a spike detection as well. We can discuss that later on. Okay, and in terms of compression ratios, just to get a ballpark estimate, these 3 plots are for different amounts of noise. So as you expect, as you increase the amount of noise, the compression ratio curves will generally go down because there's a lot of spurious spikes. Yes, maybe you there?
Why do you say that spike sorting does not help you in decoding?
The reason I say this is, if we have enough number of probes from which you are getting data, your decoding accuracy, we found, does not change too much. If you have very few probes from which you are getting data, then spike sorting helps you increase the dimension of your input. There it helps a lot. But for these channels, we are using like 96 channel probes. 96 channel data, the data that we are getting is enough for decoding finger velocity kind of stuff. And the second problem is spike sorting. Actually, the shape of the spikes, that changes a lot more from day to day than just the number of neurons that we can record from. So if you are doing sorting, then you have to do one extra step of calibration, which is again calibrate the sorter. Yeah, yes.
Yeah, so you mentioned that you take all those recording from multiple channels and you send them in one packet. So you don't care about if those are synchronized or not? So if yes, how to synchronize them?
No, so there is the packetizer will have a counter. So you are synchronizing the counts in one window, and that count is what you are saying. So it's a synchronized packet in that sense.
What are the different numbers from a PCM?
Oh, this is just increasing the time window from PCM1 is time window of t, PCM2 is time window of 2t, 4t, and so on. So basically, ballpark, what you see is for action potential rates of about 40, you would expect compression ratios about 50. So if you do this. Okay, so that was the first part. Next part, looking at spike detection. Can you actually detect the neural spikes using a spike detection circuit? And we are not using digital circuits, so I'll show you what we are doing here. Okay, again, spike detection problem is kind of trying to find out these kind of neural action potentials from the raw signal. Now, if you have a front end that's actually generating these kind of on and off pulses, and if I have to put the spike detector on the chip, on the implant itself, I don't want to go through a reconstruction and then pass it through a spike detector, because that's an added level of extra circuitry. It's better if you can actually do the spike detection directly on this pulse stream. Okay. Well, again, in this workshop, we are having work groups on spiking neural networks, right? So you can potentially think that I can use a SNN to kind of detect this kind of a specific sequence of pulses, and that should be able to distinguish it from noise, right? Yeah, indeed you can. You can do something even simpler. Basically what we are looking at is, you can see if you compare with the noise with this thing, here you have a high burst of spikes, high burst of pulses that happens for consecutive time periods, right? So you can kind of use that to say that, okay, for noise there won't be such a high burst. Secondly, there won't be consecutive periods of such high bursts. Okay, so that's basically the intuition that we have. And so the circuit that we have is something like this, compared to a conventional digital system where you pass the digital output ADC into a memory, and then this goes into a digital spike sorter that reads from the memory and sorts. In our case, we have these AER pulses coming out, and then a decoder decodes it and puts it into a memory, and this memory itself does spike sorting, spike detection, sorry, not sorting. So it's really in-memory computing that's doing it, yeah.
Why not just use a matched filter? Because you are doing a matched filter, why even go through the spike generation process? Can you use an analog matched filter and then do a...
Why go through this spike generation process?
Yeah, because you are counting, anyway you're matching, you're doing a template matching technique.
Well, template matching actually is, it means that your template is very stable. Here we are using something much more relaxed than a template matching. We're just doing counting, right? So even if due to noise over time things change, the template changes, that basic property still stays the same, that you have a burst of pulses over a period of time.
But the number of bursts can also change, right? So that's...
Yeah, the number of bursts can also change. I'll show you that it's pretty robust to the number of bursts. But if you want to match it as an exact template, that varies a lot.
Yeah.
Yeah. So basically elements here look something like this. So you have some write transistor that writes to the memory. The memory itself has a capacitor like a DRAM and a SRAM like circuit. I say SRAM like because there is a switch to cut off the SRAM. And I'll show you how it's used. So we call it hybrid RAM. It's like a combination of SRAM DRAM. Yeah.
So if you do the spike detection instead of spike sorting, you cannot distinguish between different units on the same electrode.
That is true. We cannot. But that's what I was saying is we found that is okay for decoding accuracy, does not change too much, and it's more robust. Going ahead to this actual circuit, so we can actually match the intuition to what's happening in the circuit. So if these are the event pulses that are coming in, what we are trying to do is we are trying to count the number of events in each kind of time bin in some sense, and then we are trying to threshold and see if the number of events is larger than some threshold or not. Okay? So then you can go to this vector which is having few ones in it, and then the detection is saying, okay, how many of these bins are more than a 1. Okay, so we have two sets of thresholding. One is thresholding this count, secondly is thresholding the number of ones in a certain time period. Okay. So the first thresholding happens like this. You actually shut off the SRAM using the switch, and you just accumulate pulses here on this capacitor. So it's an analog accumulation that's happening. So that's what we are doing for this counting part. Secondly, for the thresholding, we enable the SRAM, and the SRAM's threshold decides if this point is larger than the desired threshold or not. So you can directly lock in the value and regenerate this voltage up to VDD or to ground. Okay, so that creates this 1 or 0. And finally, to get the spike detector output, when you have to count how many ones are there, we just use a standard like a KCL kind of thing for in-memory computing. The SRAM drives a transistor which pushes current into this column line, and you can just add up all the currents from each of the cells and compare it with the threshold. So this plot is showing you how well this works. This color is showing accuracy. Red is basically good color. These good accuracy, and these two are the two thresholds: the threshold of the SRAM, threshold of the detector. Okay. You can see there are broad regions of red here. Okay, so it's pretty robust in terms of how you decide the two thresholds. Secondly, if you look at the voltage distribution on the DRAM, actually there's a pretty good separation between noise and spikes. So the SRAM threshold does vary a lot with process, but because of this big separation, we can still work pretty well even in scaled processes. And lastly, if you look at accuracy versus noise, you can compare the original signal. In this particular data set, the original signal, if you did spike detection, you have pretty much 100% accuracy throughout over this noise range. For the HRAM, for our implementation, it's very good for low noise case. For the high noise case, it goes down to about 90%, but that's still okay for the downstream task. The downstream task accuracy of decoding still is okay with this kind of spike detection performance. Okay, so moving on last to the intention decoder. The intention decoder for motor prosthesis, remember, if you could put it on the chip, you would get maximum amount of compression. So that's something that we have worked on for a longer period of time. So I'll show you some challenges for the intention decoder now. Firstly, again, we know it has to be very low power consuming and a low memory circuit because it has to fit inside the implant. Second, there is a data drift or a non-stationarity problem, so you need frequent retraining. Stuff that happens is over time, some electrodes, as I mentioned, there is scar tissue formation, so the impedance increases, so over time some of the electrodes even drop out, you don't get too much data from it. And secondly, if you have to retrain, you need to know, you have to detect this drift. Okay, so how do you detect that there is non-stationarity? An example from our case, in this case the primate was trained to move a wheelchair in 3 directions, right, forward or left, and there was a stop. So you can see from session 1 to session 2, day 1 to day 2, the tuning curves vary a lot from that same neuron. Right? So there is indeed a lot of non-stationarity, and one of the reasons is this micro motion of these electrodes, because when the monkey moves a little bit, the electrode will move, and the neuron that you were recording from on day 1, for example this one, may actually move out. Okay. At some later time, if this comes back in, this neuron may again start putting information back on the electrode. Okay. And of course, there is also this question about how you can distinguish from background neural activity. Why I say this is when we are having a data set and we try to do this decoding offline, it's a very curated data set, right? It's only taken by snipping out parts of your trials. But if you're using this all the time, there is data that's going to the decoder all the time. So you need to know when the person intends to use the arm and when not. So it's very important to distinguish background activity from the actual desire to move the object. And lastly, I put this part, this is flexibility to add new outputs, because if you're putting a decoder in the implant, it's already there, right? And it's a chronic implant. Maybe 2 months down the line, you decide that, okay, I want to decode for something else. Then the decoder circuit should be flexible enough that you can change it. Okay? So these are some of the challenges that you face when you want to put these decoders on the implant. Okay. So what did we do? We chose this kind of architecture, which is reservoir computing architecture, or similar to liquid state machines, which is basically what happens is the inputs that are coming in, they go into a large randomly connected recurrent network. It can be recurrent or non-recurrent. In the machine learning community, there's this thing called random vector function lick or extreme learning machine, where the recurrent connections aren't there. But basically the point is you are creating a high dimensional projection, and these weights of these neurons are all random and fixed, no training in here. From this output, you can actually train a second layer to decode whatever quantity you are interested in. Okay. Because you are only training one layer, the training becomes very simple. You can actually do very fast training, and you can actually add new outputs to this layer without changing the reservoir at all. Okay. So that's why we chose this kind of an architecture. How to distinguish from background neural activity? We actually did something where we trained separate decoders explicitly to decode for background activity versus desired activity. Okay. And then separately we trained a second decoder to say, okay, if you want to move the wheelchair forward, left, right, whichever direction, decoder number 2 is trained for that. And at the output, we combine the results of these two decoders. So the decoder that's deciding on whether it's background activity or not is kind of like a gating mechanism that allows the system to put the data out or not. Okay, so you combine the two data in this way. So you can see sort of here, this is the raw neural data, and this is the predicted onset of movement, and this is going to gate whether the output will go out or not. And there are some other tricks that we did to improve the performance. I won't go through details. In terms of the actual circuit that we did, because the large fraction of computation that's doing the random projection requires randomness and is fixed, we actually used very simple tiny analog current mirrors, where the mismatch in the current mirrors is being used to create the random weights. Okay, so the mismatch is not a problem here, it's a feature. Okay, so this big array actually uses mismatched analog devices which are very tiny. So it helps you save area and still does the thing. And then we did some other co-design tricks in the training to induce sparsity in the hidden layer. Okay. I talked about this electrode dropping over time. To counter this, we also did some algorithmic tricks for electrodes from which we are getting data. We actually also used time delayed data from the past to increase the dimension of the input that's going into the decoder. So with that, we were able to achieve classification accuracy in the decoder, in the hardware, totally comparable with software. Okay? And this is very important in this area of biomedical in general. In a lot of times in machine learning hardware, when you will see a case where people say that I can get 10x reduction in energy by doing a 2% reduction in classification accuracy. But in biomedical systems, generally, you cannot allow any kind of reduction in performance because it's really, really serious for the patient. Okay, and also this shows you how extra information from time delayed versions of the past helps you in improving decoding accuracy. especially when the number of neurons that you're decoding from is very less. Okay. All of this was done within a power budget of about less than a microwatt. So this was doing about 50 classifications per second. It amounts to about 8 nanojoules per class, which is very low power, good enough for implantation. Okay. And this will show you a video of the decoding. I don't know if you can hear this. The sound that you hear is actually the sound of action potentials. Like Arun was saying, most beautiful sound in the world. So, and what you see here is the output of the decoder. This is saying whether you will move or not. And this is the type of movement that's decoded. F4 means flexion of the 4th digit. So in this case, this was looking at finger movement. So flexion and extension, and which digit number, which of the fingers you're moving. This is extension of 4th digit and so on. Okay, so let me move on. So what I showed earlier, this work was pre-recorded data pushing into the system. Okay, but if you really want to do this, you have to do closed loop decoding, because that is what is going to happen in the real life. Okay, so that's what we did next. This decoder was actually interfaced with a primate doing a joystick task. So it's like a radial out task where it's moving out to different directions. And the output of the decoder was used to move a cursor on the computer screen, and the monkey is getting visual feedback by looking at the movement of the cursor. So what you see here in these two plots is this mean trial completion time. The first blue one is hand controlled joystick, which is when the monkey is just moving the actual joystick, making the actual motion, and we are decoding the data. And the second one is entirely brain control, when the monkey is just thinking about it and not making the movement. Okay? And what you can see is in all the cases, the speed that we have is about 85% of hand control, so it's pretty good. The second thing you need to look at is the mean trial success rate. And again, we see for the neural control case, the trial success rate is very close to the hand control case. Okay? So which means the decoding is working pretty well. Yes?
So if you're decoding, I'm assuming like from the motor cortex, wouldn't you be able to decode before they move? Like why is it happening with a longer latency? Or is it the time to decode?
It's a time to complete the task, meaning the time taken to reach the target. Yeah. So this is kind of a video of that. You can kind of see a picture of the monkey sitting here. And this is again a restrained setup, not like the free setup that Arun has come up with. And you can sort of see that in this case, the cursor moves towards the right. So this is a trial success. And then again, after some while, randomly the dot is going to show up at some other point. And again, this is on the top. So again, you can see the cursor moving up on the top and so on. Okay. Again, I should give a caveat. Every day it doesn't work so well. Okay. Okay. So again, coming back, I'm almost out of time. So I'll just rush up a little bit here. Coming back to why we were doing this. Okay, we were doing this for compression, right? To make sure the data rates are good enough. So what this plot is showing you is if you keep on increasing the number of channels from 100 to 1000 to 10,000, each of these bars is telling you data rate in bits per second. Blue is raw data, red is compressive sensing. Some of you may be aware about this. Is one way of compressing the raw data. The yellow and purple, these are like spike detection. If you do spike detection, how much compression you get. And the green one is the decoder. Okay. So what you see is indeed these two dashed lines are two commonly used wireless transmitters in implants. Okay, the data rates that are allowable. You can see that if you use compressive sensing, you very easily get out of this range. Okay, beyond like 1000 channels. If you're using firing rates or spike detections, that's okay, but after about 10,000 channels, you start getting out of range. But if you're using the decoders, indeed you can keep the data rate low below this range for even up to 10,000 channels. Okay, so it's indeed a very nice way forward. Okay, so now, yes?
What's the Amdahl's law here of this? Where are the amplifier powers? So you need an amplifier, right?
That's true. There is an amplifier power part. So here I'm just talking about data rate, meaning what is the raw amount of data that you can even throw out. So it's not even talking about the power savings at all, like what is possible. Okay, so now we can actually flip the thing and think about what can brain-machine interface give back to neuromorphic. Okay, and so there has been a discussion in the community for a while about what are good benchmarks for neuromorphic systems, neuromorphic algorithms, and we believe that brain-machine interface is a great benchmark. So there was a big effort over the last year and a half, which was called NeuroBench. This was an effort coordinated by Harvard. It was across many universities, many industries across continents, where we were trying to come up with what are good benchmarks and what are good benchmarking tools. Okay, so basically we have two tracks here. One is an algorithm track and one is a system track. So the algorithm track is trying to optimize different algorithms on different data sets and tasks, and they're measuring how good the solution is using some metrics. These metrics are kind of informed by what we think are good metrics to estimate how an actual hardware system will perform. And then separately you have a systems track where you can evaluate these algorithms on these data sets and actually come up with what are the hardware numbers when you run these algorithms on this hardware. Okay? And then of course, hopefully there's a lot of talk between these two tracks, right? We keep on updating the metrics and we keep on updating the algorithms according to this. So again, in this workshop, we have a work group where we are using NeuroBench. So if you're interested, I think Vincent, my student who did this, Vincent, maybe you can say hi. So he kind of did this whole work. So there were 4 different tasks that were finally chosen after many months of debate. So this work on motor prediction is what we ended up doing, and I'll show you some results that came out from this collaboration. What we are doing here is we are predicting fingertip velocity from cortical recording. So a primate was doing finger movements on a grid of I think 8 by 8 or 16 by 16, I forget what, and they were trying to move it towards a target that's being shown on the screen. Okay, so the task was to decode this velocity of moving the fingers. What we did here is we tried to, in this community we talk about SNNs are very energy efficient. And then if you go to the machine learning community, they'll say that machine learners are much better in accuracy. So, which one should we choose? So to kind of answer that question, we took the same data set and tried many different algorithms on the same data set, tried to compare their results using A, how accurate they are, and B, how many computes are needed per classification and how much memory is needed. So basically, we are going to compare ANN type of networks with spiking neural networks and also with traditional signal processing. So in this area, Kalman filters, for example, have been used for a long time. Okay. So what do you think? Which one will win? Kalman, right? Yeah. Okay. Does it not really true? The Kalmans actually had a very, very large amount of computes because you have to update the matrix all the time. And if you did a steady state Kalman, the performance was very poor. So finally, what happens if you see here in this picture is showing accuracy in the bottom. This is using R-square regression, and y-axis is number of operations, number of computes. We have a similar curve for memory versus accuracy, but the trade-off is more or less similar. So I'll just show one. Each of these dots are different types of networks. Okay. What you see here is there are some blue dots and some yellow dots. Finally, what ended up happening is we see if you combine something like an SNN with a traditional filter, the combination ends up being very good for regression like tasks like these. Okay, so what you see here is in terms of the performance, best way to compare them is to treat it by looking at a Pareto curve. What is a Pareto optimal curve? Where is the frontier? Okay. So what you kind of see that SNNs are indeed very good. They are on the Pareto curve, but their accuracies are on the lower side. So we cannot absolutely say that SNNs are the best or SNN plus filters are the best. Near the top, what you see is you have some LSTMs. These squares are LSTMs. Recurrent neural networks like LSTMs actually end up giving you very good accuracies, but their number of computes are orders of magnitude more. Okay, so that's basically the trade-off. Again, you can, using this kind of a analysis, you can kind of say which one is better instead of just saying, you know, LSTM is better or SNN is better. You can actually qualify that by saying, okay, both are optimal in some way. They are both on the Pareto optimal curve. Okay, so I think I'm out of time, so I'll quickly look at future directions and then we'll end there. So in terms of future directions, one of the important things is, like I said, this non-stationarity. Right now we have some methods, some training methods that are robust to non-stationarity, but you still need to retrain once in a few days. So if you could have a self-calibrating or a self-learning implant, that would be the best solution. So it's something that could continually learn. Okay. Again, there's a challenge here, how to determine when to train. Okay, that's kind of a challenge. Second thing is, we talked about the part where we are decoding from the brain, but what about the feedback part? So sensory feedback is very important. Again, in this workshop, we are doing a work group where we are looking at tactile sensing. So in my lab, we have started looking at tactile sensing to provide some feedback if you are using this kind of arms to manipulate objects based on the BMI output. Okay, and there are several challenges on designing these sensors, making them robust, and how do you merge the control from the brain with this sensory feedback input. Many open questions here. The third one is actually in terms of benchmark, and this one I think is very important. The benchmarks that we had in version 1 of NeuroBench were open loop benchmarks. Okay. But as I told you, like, open loop benchmarks aren't very good for BMI, and I believe closed loop benchmarks are also the way to go for neuromorphic systems, because that's where they are potentially going to shine better. Okay. So the next version 2 of NeuroBench that we are doing is actually looking at closed loop benchmarking. So what's happening here is, think about the task that I showed. So this is the target, this is my initial position. What should the primate do? The assumption here is the primate wants to get the reward, so they want to move the cursor towards this side. So you can create a vector that is kind of saying what is the primate's intention. Okay. Now you can feed this vector into a model. This OPS is, we call it the online prosthesis simulator, came out of Stanford. And basically it is a model of the neural activity that should be generated if this is my intention. Okay. And so now this can go into your decoder, and the decoding is not perfect. It's not showing you exactly this direction, it's showing you this direction is the way to go. Okay. So in this time step, you move the cursor here, and again in the next time step, you can see the desired vector has changed. So now you can pass this new vector into the brain model to generate new set of spikes, which will go into the SNN, and the whole system will continue till you converge. Now the advantage here is you are actually mimicking a closed loop system. Okay? And so I believe this will be a much better benchmark than the earlier one. So we are currently integrating this into NeuroBench version 2. And lastly, this is my last slide. So I'm sorry for that. Almost done. I think for BMI, it's also useful to rethink the tasks that we do. Okay. Why I say that? Because you're telling a person to move a cursor to the left, to the right, and so on, right? This is not really very natural to a person. If he's thinking about writing a word, potentially it's more natural if he can think about handwriting. So this was kind of a breakthrough that happened I think 2021, coming from Krishna Shenoy's lab, Stanford, where instead of telling the person to think about moving the cursor towards A, they told them to think about writing the letter A. Okay, and they decode the activity corresponding to that. And changing this task paradigm allowed them to go from 40 characters per minute to 90 characters per minute. It seems this is much more natural for the brain to generate this kind of dynamics. Okay. This is fantastic, right? You rethink the paradigm in which you are doing all your experiments. I think that's very important. I think that also gels in with what Arun was saying. When we tell the primate to do something in a restrained way, we are maybe not getting their natural reactions. Okay, that's pretty much the same. Okay, so with that, I think I should thank all my collaborators, all the students, of course, who have done all the work, and I'll be open to questions again. Thank you.